This next section, I want to talk about momentum for a moment, and particularly this equation right here. This is the law of conservation of momentum equation. And basically, it's a little sketchy here. You could rewrite this as momentum of the first object plus momentum of the second object equals momentum of the first object prime, which is the new momentum after the collision, plus momentum of the second object prime. Now this would be for an elastic collision where the objects don't stick together. There should be a minus sign here. All right? One of the things that's very important to understand about momentum is that momentum is a vector quantity, and the way you set up your equation to plug into momentum before equals momentum after is very critical. You can either add them if the objects are moving in the same direction, or subtract them if they're moving in the opposite direction. Let's take a closer look at this. So here I have two masses, two carts on a dynamics track, and you can see here that if I have a collision, the objects can move in opposite directions. In that case, the vectorial nature of them should be subtracted in the equation, so it would be P1 minus P2. If the objects can also collide and move in the same direction after the collision, in which case their momentum should be added, P1 plus P2. If you have a situation where the objects collide and stick together, we refer to that as an inelastic collision, in which case they become one object and you don't have to have the equation the way I've written it. It has to be with just a single term. So instead of having two terms for an elastic collision, we would have a separate term that would just be a single term because the carts collided and combined. So it would just be the momentum of cart 1 plus 2, all right? Which would be the mass of cart 1 plus 2 times the new velocity. Now, the other thing I want to point out here is this impulse equation. The impulse is net force times time equals change in momentum. Usually an object's momentum changes by having its speed change. So we can actually take this equation and set it equal to this one, and I tell my students, write m delta v, all right? And that way, if you're given a force and a time and we want to know, let's say, what's the final velocity, you could use this equation instead, and that would help expand that a little bit to make it easier to answer questions about impulse. Continuing on, let's talk about electricity. I really want to talk about the resistivity chart that's on the electricity page and this equation right here, resistance versus resistivity times the length of a conductor divided by the cross-sectional area. So let's take a closer look at this to kind of examine where this chart comes from and how do you incorporate it. Now I want to talk about the resistivity equation using this apparatus here, but before I do that I'd like to clear up a common misconception, and that is sometimes physics student thinks that something that's neutral can't be interact with something that is charged. And I just want to show you, I have a Mountain Dew can that is just neutral, and I'm going to rub this PVC pipe with a little bit of fur, and I just want to show you that even though this is charged and this is neutral, this is still comprised of charges which can reassociate so that they are attracted. For example, the electrons in the conducting metal of the Mountain Dew can are repelled away to one side, which leaves the can positive on one side, and then it's attracted. So don't think that just because something is neutral that it can't be attracted to a charged object. Now, let's talk about resistivity. I'm going to turn this on. And right now what I have is I have a piece of tungsten wire here of a certain length with a certain voltage applied across it, and you can see that I'm getting approximately, well, I better dial that down for a second. So is that about 15? And then this is a galvanometer. It's measuring small amounts of current through the wire. And if I take a different wire of exactly the same length, this is a copper wire now, I'm going to put this in here and hook it up in the circuit the same way. And you can see that that almost pegs the meter. It's much more conductive than the other piece of wire was. So where that resistivity chart comes in is that they actually took different wires and realized that for the same length and same basic characteristics, different materials allow electricity to conduct through them differently. Some are more resistive, some are less resistive. Now, the other thing that we can change is the geometric properties of the wire. For example, you remember I had 15 milliamps before, and I can actually take this wire and hook it up, let's say, halfway through, and you can see I can get more current, which means the shorter the wire is, the less resistive it is. The longer the wire is, the more resistive it becomes, and it doesn't allow as much current to flow. All right? Now, the other geometric factor that we should worry about, so that's where the length comes in. The other geometric factor we worry about is cross-sectional areas, and one of my favorite things in the world, Play-Doh. Still smells like heaven, and it reminds me of my youth. But I have a very large circumference and a much smaller cross-sectional area, and what I'm going to do is I'm just going to apply, I need a little bit more voltage for this, so I'm going to ramp it up to about 3¼ volts. And I'm going to send now applying the same voltage now to the same length of wire essentially. So I can get about 2 right there, and if I go to the fat one, you can see I can get almost 4. So cross-sectional area is important. The fatter wire has more free electrons than a metal wire available for current, and therefore is less resistive. Now let's continue with the presentation. Now if you go down to the bottom of the electricity page, you'll have the circuit symbols here that you can use to draw circuit diagrams, and you'll also have your series circuit equations and your parallel circuit equations, and they're all fairly straightforward. The only one that bothers me is this one, for the equivalent resistance of a parallel circuit. It is entirely likely that students will forget that it's actually the inverse. So I tell students to rewrite this equation: R equivalent equals 1 over R1 plus 1 over R2 ... so that it'll be just a little bit easier for them to not make a math error as a result of not calculating the equivalent resistance, but instead the inverse. Continuing on, waves and optics. I want to talk about the velocity of a wave equation, this first one right here. So let's step away for a moment, shall we, and talk a little bit about frequency, wavelength, and wave speed. So first of all, what is frequency? Frequency is nothing more than vibrations happening per unit of time or periodically. And you can see here, this is 1 hertz, 1 cycle per second of the speaker going in and out. And if I ramp it up, and increase the frequency, eventually it will beat the air rapidly enough or frequently enough to produce a wave that we can actually hear. Now obviously what's happening frequency-wise creates the wave, and then the wave propagates through the medium. Now we can't see the wave propagate through the air, but I can hook it up to this string, and I could actually send a wave through this string, and I'll increase the frequency, and eventually we get some chaotic movements, and eventually we get something interesting called a standing wave. And a standing wave is a wave which appears to be standing still. It doesn't have that typical shape. Now notice here there's a point here in the center. That's called a node, a point of maximum destructive interference, and then you have your constructive interference here. It's reflecting off from here back, and it's superimposing itself over the same. The same type of a thing happens in other devices. For example, I have just a piece of ring stand here, and I can actually I can actually vibrate my fingers over the surface and it will actually resonate with my fingers. Now, as far as the length goes, notice that this rod is short and this rod is long. So we can get a feel for wavelength and how it relates to frequency. It's inversely related because now I have a longer length for the wave that's going to sit up in this rod. With a correspondingly much lower tone. So high frequencies, short wavelengths, low frequencies, long wavelengths. So if we're going to use the wave equation to calculate the velocity of a wave, we know frequency and wavelength will vary inversely. If one goes up, the other one will go down.